The new nearly interstellar object, officially labeled as C 2025 V1 Borisov.
Could it have originated from 3I Atlas? Is it at all related?
Two icy travelers just stole the spotlight. 3I Atlas, the third confirmed interstellar visitor, and C 2025 V1, a newly discovered comet with an orbit so elongated it briefly sparked headlines asking if it might be interstellar too. Both are in the inner solar system within weeks of each other.
This object has an orbit in a plane that is almost perpendicular to the plane of the orbit of 3I Atlas.
One is definitively alien to our Sun's family. The other is almost certainly an Oort cloud newcomer, making its first close brush with sunlight. So what is different? What is similar? And what can this matchup teach us about comets from here and from elsewhere? Start with the essentials. 3I Atlas was discovered on July 1st, 2025 by the Atlas survey in Chile and quickly confirmed as the third interstellar object after Oumuamua and 2I Borisov. It reached perihelion at the end of October at about 1.4 astronomical units from the Sun and will never return. Its path is hyperbolic with a very large eccentricity and a near retrograde inclination. Its closest approach to Earth in mid-December stays a comfortable distance of about 1.8 astronomical units, so there is no hazard, only science, and a brief window to watch a visitor depart the stage forever. Now meet C 2025 V1 Borisov, discovered on November 2nd, 2025 by Gennady Borisov. Early orbit solutions show perihelion on November 16th at about 0.463 astronomical units from the Sun, inclination near 113 degrees, and eccentricity a hair above 1, roughly 1/96. That last number is why it grabbed attention. Values just over 1 can look interstellar at first glance. In practice, this happens often for long-period comets, when the observation arc is still short and non-gravitational effects from outgassing are not fully modeled. As more measurements arrive, many such solutions settle back to eccentricity at or below 1, pointing to an origin in our own Oort cloud. How do astronomers prove an object is interstellar rather than a first-timer from our distant reservoir of comets? The answer is patient measurement. They extend the tracking arc over many nights, fit the orbit while accounting for small thrusts from gas jets, and compare independent pipelines from the Minor Planet Center and JPL. If the eccentricity remains comfortably above 1 after all that, the body is unbound to the Sun and is interstellar. That is the case for 3I Atlas. By contrast, C 2025 V1 sits in the zone where early solutions often appear slightly hyperbolic, but are expected to relax toward a bound orbit once the math includes more data and realistic jetting forces. Inclination and geometry help tell the story, but do not decide it alone. 3I Atlas follows a very high inclination, nearly retrograde path that lines up with an origin beyond the Sun's family. C 2025 V1 also carries a steep tilt, but steep angles are common for Oort cloud comets, since that cloud surrounds the solar system in a roughly spherical distribution. A dramatic plane of motion makes the comet interesting to observers, yet only the energy of the orbit and its stability after modeling can award the interstellar label. What about what we actually see at the eyepiece and in images? 3I Atlas has displayed a visible coma and tail, with brightness and color behavior consistent with gas becoming active near perihelion. As it reappeared from solar elongation after perihelion, observers noted tail geometry changes and reports of an antitail. An antitail is not a physical reversal of dust motion, it is a perspective effect. A sheet of dust aligned edge-on to our line of sight can make the tail appear to point sunward, even though radiation pressure still drives dust away from the Sun. This geometry occasionally aligns for solar system comets too, so the feature is not unique to interstellar objects. It is a nice reminder that viewing angle can reshape what we think we see in the sky. C 2025 V1 sits in a different observational regime. Around discovery and into perihelion week, its brightness is around magnitude 13 to 14, which means telescopes are required. That does not make it dull. The closer perihelion distance hints at stronger solar heating and the possibility of rapidly changing activity levels. Sun-skimming orbits can produce quick changes in the coma as different volatile ices respond to temperature. In the days around perihelion, small outbursts may alter the apparent size of the coma, the tail length, or the color balance as gas and dust contributions shift. Those are the moments observers and photometrists watch closely. Speed is another difference people notice. NASA highlights that 3I Atlas is racing through the solar system at roughly 130,000 miles per hour. High speeds alone do not prove interstellar origin, since any comet accelerates near the Sun. What matters is the excess speed after accounting for the Sun's gravity. Interstellar objects carry a permanent surplus. They arrive fast and they leave fast, even when they are far from the Sun. That surplus is built into the hyperbolic solution that survives careful modeling. For C2025 V1, the high speed near the Sun is mostly gravitational, not proof of an interstellar past. If both comets can be faint to casual observers, why is the science community energized? Because a side-by-side comparison under nearly the same solar conditions allows a cleaner test of models. With 3I Atlas, we can study a body shaped by another star system's birth environment, and we can watch how its dust and gas respond to our Sun's heating for a single pass. With C2025 V1, we get a control case that likely represents the first inner-system pass of a native comet drawn in from the Oort cloud. Differences in tail texture, gas species, dust size distribution, and non-gravitational accelerations feed directly into how we model comet physics and origins. It is worth addressing a common misconception. Some viewers assume any eccentricity above 1 means interstellar. In reality, measurement uncertainties, short arcs, and unmodeled jetting often bump early fits slightly over 1. Analysts expect that for many new long-period comets. That is why official channels wait for longer arcs and refined models before declaring an object interstellar. The system is deliberately cautious. In the present comparison, official messaging is clear. 3I Atlas is interstellar. C2025 V1 is not confirmed interstellar and is best treated as an Oort cloud comet unless and until the final numbers say otherwise. What should observers expect if they want to look? C2025 V1 is a telescopic target for most amateurs, with brightness around magnitude 13 or 14. Larger instruments and dark skies will help. 3I Atlas is also a telescopic object post-perihelion. Neither promises a naked eye spectacle at this time, and both benefit from dark locations, patient star hopping, and up-to-date ephemerides. Watch for changes rather than a single snapshot. For 3I Atlas, the changing viewing geometry as it climbs away from the Sun should continue to reshape the tail and coma structures. For C2025 V1, the days around perihelion can deliver quick shifts in activity as fresh surfaces are exposed and ices vent. Let us put the differences and similarities in one place. Origin is the headline. 3I Atlas is interstellar based on stable hyperbolic solutions that incorporate outgassing. C2025 V1 is most consistent with our own Oort cloud, given its marginally hyperbolic early solution, and the well-known tendency for such values to relax as more data arrives. Geometry diverges too. 3I Atlas reached perihelion near 1.4 astronomical units and stays far from Earth at about 1.8 astronomical units minimum distance. C2025 V1 dives deeper, with perihelion near 0.463 astronomical units, yet has remained faint for now. Kinematics also separate them. 3I Atlas retains interstellar excess speed and is on a one-pass exit. C2025 V1 moves fast near perihelion because the Sun's gravity speeds every inbound comet, not because it hails from another star. At the same time, they share core cometary physics. Both are icy bodies that awaken under sunlight, build Comean tails, and exhibit structures shaped by dust size, gas production, and solar radiation. Both can display antitails or other surprising features when geometry lines up just right. And both demand continuous orbit updates as astronomers ingest new astrometry and refine non-gravitational parameters. That is part of the fun and part of the challenge. The story is written night by night. Where does this leave the idea of a comet that is nearly interstellar? It is a phrase that sounds exciting, but orbital mechanics does not really recognize a middle ground. Either the final, well-modeled solution is unbound, or it is bound. Slightly above 1 during the first week of fitting is not a category. It is an artifact of limited data. That does not make C2025 V1 any less interesting. In fact, it makes it a perfect comparison target. We get a steep dynamic orbit that is native to the solar system to set against a clean interstellar case. When the goal is to understand how comets behave near a star, a well-matched control is exactly what you want. There is also a practical reason this comparison matters. Spectroscopy and photometry depend on signal-to-noise that can be marginal for faint comets. Having two objects in play within weeks means telescopes can use similar instrument setups, similar solar phase angles, and similar background conditions to collect data. Researchers can look for differences in gas species such as cyanogen, diatomic carbon, or oxygen lines, differences in dust profiles inferred from color, and differences in how non-gravitational accelerations evolve as the comets rotate. These side-by-side datasets help separate what is due to origin from what is due to the immediate solar environment. For viewers following along at home, there is a watch list worth keeping. C2025 V1's perihelion on November 16th is the key date for potential activity spikes and for updated orbital solutions in the days afterward. If the comet flares, fresh outgassing terms can nudge the fit and slightly alter the post-perihelion trajectory within the uncertainties. Another reason professionals recompute solutions frequently. For 3I Atlas, the mid-December geometry improves for many locations as the comet moves away from the sun's glare, giving amateurs a better chance to tease out tail structure with stacked images and careful processing. Professional teams will continue to post revised elements via JPL and the Minor Planet Center and to release spectroscopy as signal improves. The main takeaway is straightforward. Side by side, 3I, Atlas, and C2025 V1 offer a rare natural experiment. One is proven interstellar, skimming the sun wide and gliding out forever. The other is almost certainly an Oort cloud first-timer, diving deeper and staying faint but scientifically rich. The comparison is not about choosing a winner. It is about how gravity, sunlight, rotation, and dust physics sculpt two superficially similar comets into different stories. As the observation arcs lengthen and models settle, expect the labels to sharpen, the uncertainties to shrink, and the science to get more precise. With comets, the narrative can change in days, which is exactly why this pair is so valuable right now.